Hey everybody, in this set of videos I'm going to go over how to transform graphs using transformations of vertical and horizontal reflections, compression, stretches, and shifts. So I'm going to start by going over how to transform linear equations as opposed to graphing linear equations using the concept of, say, y equals mx plus b, which is probably what you were taught maybe in, say, middle school or so. I think that by introducing linear equations from a transformation standpoint is a perfect way to dive into transforming all of the parent functions in this exact way. It is going to take a little bit of like brain resetting, so just hang in there. And if there's a synchronization issue with my two cameras going on, sorry, I did everything I could to try to fix it, and I don't think it is totally fixed right now. Okay, so let's dive in. There will be 4 examples. I'm going to try to keep this under 10 minutes total, so you can jump ahead to see one of the 4 examples, okay? So the first example on each of these chapters is going to be the parent function. In this case, that is y equals x. I'm going to rewrite it because the printout is not great. Y equals x is known to be what we call the identity function. I'm not going to write down every single word or phrase, so add it to your notes as you see fit. Y equals x is known as the identity function because y is equal to x and they are exactly the same. Nothing has changed. Now, this linear equation can be identified from x being to the first power in the numerator, yada, yada, yada. Hopefully, we all know that at this point. How can I write this using a, b, h, k? 1 x minus 0 plus 0. So if you look up here or on the screen, a, b, h, k, they're going to be set up the same way. B and h live inside what I call the backward house. And the backward house, everything is sort of backwards. We shall chat about it in a second. Minus 0 plus 0 is your shifting. Inside is left, right. In the house is left, right. And plus 0 outside is up, down. So specifically, what am I talking about? This sheet right here more or less will show you how everything works. So if you need to look at it over here, the vertical transformations are going to be coming from a and k, which you see on f, any function, excuse me, any function, are located on the outside of what I call the house. The thing housing b and h is usually your main function. So in this case, they're inside parentheses, so the first power, they're linear. The horizontal stuff, b and h. And if you read through, pause, do what you have to do, you'll see that. And then the visual depictions of how the A and B specifically, which seem to be the hardest for everybody, how they specifically work visually is over here. So take a second, write that down for yourself if you don't have that somewhere already, and it's going to help you out. Okay? So anything I refer to transformation-wise is all on this sheet. And if you're watching this video, I'm assuming you have done work with this in the past. If you are brand new to this, just hang in there. All right, so here, minus 0 plus 0, that means I did not move left, right. I moved left, right, nothing. And that I did not move up or down. So that means I moved right 0, up 0. So I'm going to put a yellow crosshair, plus sign, little mark right there to kind of calibrate. This is where my graph is centered around. Even though it does happen to be at the origin, I can refer to it, say, as my new origin, where I'm moving my graph to. So that point is right there, 0, 0, y and x both equal 0 at that point. Now, where else do y and x equal each other? At 1, 1, at 2, 2, at 3, 3, at 4, 4, but also at every decimal increment value in between, and the same idea with both being negative. The end, okay? That is our y equals x, okay? What else can we talk about over here? And behavior. From a visual standpoint, if you describe it in behavior, we describe the left side and the right side. And in a polynomial sense, we tend to say, for something like this, down, as in down on the left, it's going down on the left, and up, it's going up on the right. Without visually, just looking at the original equation, we have a positive leading term, 1, x to an odd power. Positive leading term, what does that do? It means your graph is finishing up on the right. What about an odd degree of that polynomial? It means that the left side starts in the opposite direction, so in this case, down. So there you go. You could also look at it as a limit standpoint. What is the limit as x approaches infinity? As x approaches infinity, what does the function do, or the y value do? It goes up, so also infinity. What happens as x approaches negative infinity? As we go to the left, as x goes to the left, y also, the function, goes to negative infinity. That would be the answer to the limit question. Domain, the domain is asking you what x values are being used. From left to right, we cover every x value from negative infinity to infinity, and range from bottom to top is the same situation, negative infinity to infinity. So that is the end of introducing the, I lied, symmetry. The type of symmetry we see here is known to be odd symmetry. Odd, all right? Coincidentally, a lot of the functions that have parent functions with odd symmetry have an odd degree. The odd symmetry means that the output we get from any input, if we plug in, say, some positive x value, the output we get will be the opposite of what we'll get if we plug in the negative x value. Visually, if I put a push pin into my graph at the origin and rotate my graph 180 degrees, I will get back the same picture. Algebraically, as a rule, the f of x, plugging in some x value, will yield you the opposite results that you would get from plugging in that negative version of the x value. I could rewrite this rule by dividing both sides by negative, so you may also see it written as the negative f of x equals the f of negative x. They mean the exact same thing. Next, here is actually, why am I doing that? We could say here. Here's our first example. I'm going to rewrite it. Y equals 2 parentheses x minus 0 minus 3. You don't see b manipulated very often, so forgive me for not indicating that it is a 1 in this case. I will bring it up when I feel it's necessary. So what does this mean about our graphing situation? So I rewrote this in more of a format like that. That means I move right 0 and down 3. The 2 is a vertical and only vertical. It's not a dilation where it's getting bigger or smaller in all directions. A vertical only stretch of 2. And if you remember the information I had on the screen before, if a is larger than 1, it's a vertical stretch, so it's only going to stretch it vertically. So the first thing I'm going to do is mark up where I'm sort of recalibrated to. I moved left, right, 0. I moved down 3. So that means I'm recentered right about there. So the big dot in the middle of that plus sign is now right here. Ooh, I'm bleeding through the page, not good. Now, vertical stretch, this is important. It's not up 2 over 2. That would just be a dilation. It's the same as up 1 over 1. Now I'm stretching from doing this point. I'm going up 2 over 1. As easy as you think it is, the concept is what matters. So do you understand? I'm only changing in the vertical direction. If I were doing a horizontal stretch, that's different. A vertical stretch makes your graph taller and more narrow looking. A horizontal stretch would make it wider. So a horizontal compression is more comparable to a vertical stretch. They're not always the same thing though. More often than not, they're not the same thing. So down to left 1 as well. Connect. This is going to continue forever on the right, and it's going to continue forever on the left. That is the end of this example. Pause, copy it, do what you gotta do. Let's go to the next examples. Next, I have 2 more right here. This one over here, what are my transformations based on this, okay? Don't mess this up. You're going left 4, down 1. If you're not sure, go back to that picture I had on the screen before of all the rules, okay? In another video, I can go over why, but I'm just trying to hit all the major points, okay? So there's that. Now the negative, okay? The negative, what is that going to do? That is a vertical, because again, it's A, it's not B, a vertical reflection. Now this is annoying, but when you have a vertical reflection on an odd function, it looks exactly the same as a horizontal reflection on an odd function. If I flip this graph right over here, if I flip it up down, I will get the exact same picture as if I flipped it left right. What is a horizontal reflection? This way. Stop and think about it. A horizontal reflection is not reflecting over a horizontal line. A horizontal reflection is flipping in a horizontal direction, okay? That's a horizontal reflection. So I'm just gonna take a second. If I highlight, just to really indicate the difference, if I have that highlighted side of my graph, a horizontal reflection means B is negative. That would be the highlighted would be in this quadrant over here, versus a vertical reflection. Vertical reflection is in the vertical direction, the up and down switch, it's over the x-axis, that highlighted pink part would be down here. Does it matter right now? No. Will it matter in other graphs? Yes, particularly the square root graph. Back over here. So it's a vertical reflection. What else do we have going on? We have a 2/3 for my A value. If you remember, when the A, absolute value at least, of A is between 0 and 1. So this is going to give us a vertical compression by a factor of 2/3. Now, I'm going to go into a lot of what some of you might think is unnecessary detail. Sorry. So let's go and get started. So left 4, down 1. Left 4, down 1. I'm recalibrated to this spot right over here. That point is right there then. Now, 2/3, vertical compression. So instead of down 1 over 1, I'm going to go down 2/3 over 1, 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 down 2/3 over 1. And you might be thinking, what the heck is happening? I'm only compressing it vertically by a factor of 2/3. So instead of down 1 over 1, because of that flip, I'm going down 2/3 over 1. However, because this is a linear parent function, going down 2/3 over 1 3 times is exactly the same as going down 2 and over 3. In the case of a linear equation or an absolute value of x equation, it does the exact same thing. Whether you go down 2 out 3 or down 2/3 over 1, and I will only say that once. So there you go. When you get to the absolute value video, I will try to not repeat that so you don't have to listen to me again. The end. That's the end of the example. And lastly, we have this one. I can stick a plus 0 at the end. So that's H, that's K, that's A. So this one, it moved right 3, up 0, and no flip, but a vertical stretch of 2, exactly like example B. So where is my recalibrated center going to be? It's going to be to the right 3, so right over there. Then all I'm doing is applying my vertical stretch of 2. Now I know this one's not that elaborate of an example. I just wanted to do it to sort of do two things. One, compare it to example 2b to see the similarities and differences in appearance of the equation versus how they result and work out. This is 3, 0 right over there, and that is 0, -6. So they look alike. There's 1D. There's 1B. As equations, at first glance, they look quite similar. Another thing, if you were to kind of go and do it the old school way, y equals mx plus b, y equals distribute the 2x minus 6, you would start off at -6 as your y-intercept, rise 2, run 3, rise 2, run 1, rise 2, run 1, yada yada. And you would get the exact same graph. So yes, they are the same, but that will not always happen. That will happen in the case of a linear equation because of the simplicity of the graph. So how am I for time? If you feel like you wrap your head around everything I'm talking about, even if you still don't see the point of any of this, go ahead, give a thumbs up. Question, comment, go ahead, leave in the comment section. Thumbs up, comment. Look for more videos. The next one I'm doing is absolute value. I'll put them all in a playlist, and adios.